This video will wrap up aldehydes and ketones. So in the last video, we looked at hydrates, acetal formation, including cyclic acetal. We looked at the formation of imines and enamines. This would just simply be imine formation with this particular amine. We looked at hydrazine and imine formation and how that can be reduced to a CH2 group. And then in this video, we'll look at hydride reactions, Grignard's, addition of cyanide, something called a Wittig reaction and a Baeyer-Villiger reaction, and sulfur nucleophiles. So let's begin with sulfur nucleophiles. We can react two equivalents of thiol to form what's called a thioacetal. This is directly analogous to how alcohols react with ketones and aldehydes. And if we have a dithiol, we would get a cyclic thioacetal. The useful thing about thioacetals is that they can be converted to alkanes when reacted with something called rainy nickel. So this is another method for reducing a ketone or an aldehyde to the corresponding alkane. The other method he learned was using hydrazine followed by the Wolff-Kishner reduction, but you can alternatively make the thioacetal following up with the rainy nickel treatment. Hydrides such as lithium aluminum hydride and sodium borohydride will reduce carbonyl-containing compounds, and these will be carried out under basic conditions because hydrides are strong nucleophiles. So this is a review of something you've seen before, but essentially the hydride is going to attack the carbonyl carbon, breaking the pi bond, and then in the second step you have a proton transfer from water. And you can alternatively just draw an H- in your mechanisms. I think that's easier than drawing it from the aluminum hydride complex. Also recall that Grignard reagents attack ketones and aldehydes to make an alcohol with a new carbon-carbon bond. So here, if we add CH3, we can think of the Grignard as the alkyl group with a negative charge. So that's going to attack the carbonyl carbon, breaking the pi bond, pushing those electrons up onto the oxygen, and then that second water step. So after this, you would have this intermediate with a negative charge on the oxygen. So in the second step, the water step, you add some water, and that's going to provide the proton for this OH group. And the mechanism, as I just showed you, is essentially identical to the hydride. You have the nucleophile attacking, breaking the pi bond, and then protonation occurring with the water step. In cyanohydrin formation, cyanide is the nucleophile. So cyanide looks like this with a negative charge on the carbon. And typically we use HCN in combination with potassium cyanide. So in this, the cyanide's the good nucleophile. It attacks the carbonyl carbon, breaking the pi bond, and then the HCN that's also present in the reaction protonates the O- and regenerates the cyanide. Notice here that we don't have to do a separate water acidic workup because HCN serves as a source of protons. Because we want this under basic conditions, potassium cyanide is used in conjunction with HCN, and in this way there's more cyanide than H+. Notice that you could form a new chiral center, such as this reaction shows, and if you do, you would get both enantiomers, you would have racemic products. The Wittig reaction is a very useful way of converting a ketone or an aldehyde to an alkene. So here, see that the carbonyl is now the carbon in the product of a new alkene. So if we look at the bottom reaction, this carbon is this carbon, and the second carbon of the alkene comes from what's called the Wittig reagent. So it would come from this reagent here. So let's talk about the Wittig reagent. It's something called an ylide, and in particular it's a phosphorus ylide. So an ylide is defined as a neutral compound that contains a negatively charged atom adjacent to a positively charged atom. So it's overall neutral. So here in the Wittig, we have a negatively charged carbon adjacent to a positively charged phosphorus. And there are two resonance structures. So sometimes you'll see the Wittig reagent drawn like this. Sometimes you'll see it drawn like this. Both are fine. And then the mechanism is like a 2+2 cycloaddition between the Wittig and the carbonyl group. So here's the mechanism. It's simply a two-step mechanism, but the charge-separated resonance form is what's most useful in drawing the mechanism. So draw an arrow from the lone pair on the negatively charged carbon to the carbonyl carbon, and then the pi bond will break and form a new bond with the positively charged phosphorus, and that gets you to this oxaphosphatane intermediate, which then fragments. So the phosphorus carbon bond breaks, and those two lone pairs form the new alkene pi bond, and the carbon oxygen bond breaks, forming a pi bond with the phosphorus. And you get the new alkene and triphenylphosphine oxide as a side product. Now, how would you make a Wittig reagent? So you start with an alkyl halide, such as methyl bromide shown here. Then you add triphenylphosphine. pH stands for phenyl, so that would be a phosphorus with 3 benzene groups attached to it. And then after that you add something called butyllithium, which is a 4-carbon alkane that is negatively charged on one end. And it is an extremely, extremely strong base. So in the first step, we're going to do an SN2 reaction where the phosphorus is the nucleophile. So it attacks this carbon and kicks off the halogen. And then you get to this intermediate, which is a phosphonium salt. So in the second step, you add butyllithium, also called Buli, which is really, really, really strong. And you need a super strong base because it needs to pluck off this hydrogen to form the ylide. And then you get the Wittig reagent as shown here. And note that since the first step is SN2, primary halides would work easier than secondary halides. With the Wittig reaction, if it is derived from a simple alkyl halide, the Z-alkene is favored. So if we take this Wittig reagent, so this carbon and the two things attached to it will be what essentially replace the oxygen of the carbonyl. And in the major product, we're going to have the Z-alkene geometry. So notice here, the high priority groups are on the same side, which is why this is Z. This is high, this is low, this is high, this is low. If the Wittig reagent contains an electron withdrawing group like an ester, some carbonyl containing group, then we get the opposite double bond geometry as the major product, so we would get the E double bond geometry in that case. The electron withdrawing group in this example, the ester, is going to stabilize the ylide, and it's essentially stabilized through resonance. So if we look at the ylide in its charge-separated form, we can see that having that ester, you can actually draw resonance structures where you delocalize that negative charge. And then if you think about that, you can understand why this benzene ring would also have a stabilizing effect, even though we don't think of it as electron withdrawing. The Horner-Wadsworth-Emin reaction is very similar to the Wittig in that it is going to form an alkene, but it uses this reagent, known as the Horner-Wadsworth-Emmons reagent, containing a phosphonate ester. The HWE reaction gives an E-alkene as the major product, just like stabilized Wittig reactions. If we look at this alkene molecule, we can examine 2 different routes to making the alkene using a Wittig reaction. Through route 1, we would start with this ketone and this Wittig reagent. Through route 2, the right half would come from the formaldehyde and the left half would come from the Wittig reagent. So the question is, which route is better? Consider the alkyl halide needed to make either of those Wittig reagents. So let me know in the chat, route 1 or route 2, which would you use and why? The final reaction is the Baeyer-Villiger oxidation. In this, you take a ketone or an aldehyde and you insert an oxygen between the carbonyl carbon and the neighboring alkyl group. And here is the mechanism. So we're going to use a peroxy acid, which has an oxygen-oxygen single bond. So that oxygen attacks the carbonyl carbon, breaking the pi bond. And then this is where it gets a little bit odd. So the carbonyl oxygen is going to grab this nearby hydrogen in an intramolecular proton transfer, and then a rearrangement occurs. So in the rearrangement, the negatively charged oxygen reforms the pi bond between it and the carbon, and then this R group is going to migrate. So it's going to move over with its 2 electrons to form a bond with that oxygen in red, and then the remainder of this portion leaves the molecule. And when it leaves, when it collapses, it's going to leave as this carboxylic acid. If you start with a cyclic ketone, then you get a lactone, which is the name of a cyclic ester, as the product. But the question is, if you have an unsymmetrical ketone, what is the rate of migration? So which side would you put the oxygen on? And the rate of migration is that a hydrogen is going to migrate faster than a tertiary carbon, which is going to migrate faster than a secondary carbon, which migrates about the same as a phenyl group or a benzene, which will be faster than a primary, which will be faster than a methyl. Let's use this trend to determine products. So here we have a ketone with an isopropyl group on the left and a methyl group on the right. So this isopropyl group would be secondary because this carbon is connected to 2 other carbons. In this analysis, you just want to look at the alkyl groups. Don't say, oh, that's tertiary because it's also attached to the carbon of the carbonyl. We're just focused on the alkyl group itself. And then that means this would just be a methyl. So we have a secondary alkyl group versus a methyl. So the secondary is going to be better at migrating than the methyl. So we insert the oxygen between the isopropyl and the carbonyl, not the other way around. So this is not what we get. Here, if we look at the 2 groups, we've got a phenyl pH on one side and a hydrogen on the other. So hydrogen beats phenyl, so the oxygen gets inserted between the carbonyl and the hydrogen, and now you have a carboxylic acid. So you don't get that product. Let's finish up with a couple of questions. Predict the product of the following reaction. So notice this is a Wittig reagent. So think about what a Wittig reagent does, what type of products it forms. Now let's react a ketone with sodium cyanide in the presence of HCN. What type of product would you get here? And that's it. Thank you for watching the video.